This tutorial will start with an explanation of the application functionality, and second, I will run a pre-built version of this application and explain the output, and third, I will step by step write and explain the code using an Eclipse IDE. We want to use genetic algorithms in order to discover a formula that applies the AND, OR, and exclusive OR logical operators to a combination of Boolean events. And in this case, we have 5 different true-false events. And we want to produce a calculated result that equals this expected result. So for example, one possible formula to discover here after going through a number of generations is this formula written in postfix notations, and written in regular notation it would be this formula. And we have those 3 truth tables that we are using. So for x and y, then if either or both x and y are 0, then we would get 0, otherwise we would get 1. And if either or both x or y are 1, then we would get 1, otherwise we would get 0. And for x exclusive or y, if x and y are the same, then we would get 0, and if they are different, then we would get 1. This is a pre-built version of the application. So if I go ahead and run it, we went from generation 0 to generation 3, and we discovered this formula in postfix notations, or in regular notation it would be written this way. So going back to generation 0, we have in each generation a population of 6 group of expressions. So we have in each group we have 4 different expressions. So what we're displaying is the expression and the expected result and the calculated result. So we have a fitness of 3 for this group, since the expected result is equal to the calculated result in 3 of the expressions, and it is different in this expression. So I am displaying this row or this group in table format here, and the groups in each generation are sorted by fitness. So this one has the highest fitness, and as we can see here, the expected result is different than the calculated result for this expression. And we go down here to this table where all the expected result and the calculated result are the same for each expression. Next, I'll start by creating a new project. And this is going to be running on Java 8. And here we will have an expression class, and it will be in this package. And we will also have a group class representing a group of expressions, and a population class representing a population of groups of expressions, and a genetic algorithm class, and this class will evolve the population from one generation to the next using selection, crossover, mutation, and elitism. And lastly, we will have a driver class with a main method which will be driving this application. Now this is training data that I will be initially using. Now going to the expression class, an expression could be a leaf, meaning it's either 0 or 1, or it could be made up of a left expression, a right expression, and an operator. And let me define the operators that we will be using. So AND, OR, and exclusive OR. And an expression will have an expected result, a calculated result, and a string postfix expression, and a number of operands. So for example, here we have 5 operands. And we will have get methods for the expected result, the calculated result, and the postfix expression. And we will use the number of operands we have here in order to get the operator index and the crossover point. And we will have 2 set methods for the expected result and the calculated result. And in case we have a 0 or 1 expression, we will set the isLeaf flag to true, and the postfix expression would be the string value of 0 or 1, and the calculated result would be what's returned from this method that I will be defining shortly. Let's return 0 for now. And in case we don't have a leaf expression, we'll be using this constructor that will be taking a right expression and a left expression and a string operator and a number of operands. And we will be using those to set the number of operands, the operator, and the left expression, the right expression. And for the postfix expression, it will be the left expression string value plus space plus the right expression string value plus space plus the operator. And the calculated result would be what's returned from calculate result. And we need a toString method that will be returning the string postfix expression. And finally we need two methods, one that would return the postfix formula. So let's return null for now, and the other will be returning the regular formula that we discovered. Now for calculate result, let's define this return value and return it. And two Boolean flags, a left flag and a right flag. And if the expression is not a leaf expression, we will handle it here. Otherwise, the return value will be either 0 or 1. Now going back here, if the left expression dot calculate result returns 1, then the left flag will be set to true, otherwise it is false. And if the right expression dot calculate result returns 1, then the right flag will be set to true, and also otherwise it is false. And if the operator that is that we set over here is equal to and the left flag is true and the right flag is true, then the return value would equal to 1. Otherwise, if the operator is equal to OR and the left flag is true or the right flag is true, then we also return 1. Otherwise, the return value in both cases is 0. And also, if the operator is equal to exclusive OR and the left flag is different than the right flag, then we return 1. Also, otherwise, we return 0. Now for the get postfix formula method, this is the code that would return that formula. So we will use empty spaces in order to pick up the different tokens in the postfix expression, and we will go through those tokens, and if we have AND, or exclusive OR, then we append that token plus a space to the string buffer that we defined over here. Otherwise, we append, instead of 0 or 1, we append E, and we append 0, 1, or 2, 3, or 4 in this case, where we have 5 different events that we are using, true false events. And in the case of a regular formula, of wanting to pick up the regular formula in this method, so this code will be doing that. So we do the same thing, we pick up the tokens based on the space in the postfix expression, and while we have more tokens, also here we define this stack made up of strings. So If token is equal to AND or it's or exclusive OR, then we pop from the stack and put it in right, and do a stack.pop, put it in left, and then push onto the stack parentheses, and in between there we have the left and the token, the space, and then the token and space and right. And if we have 0 or 1, then we push onto the stack E and 0, 1, etc. And we return stack.pop. So this should do it for this class. Next, the group class will have an array list of expressions and a get method for this array list. And the fitness, and the get fitness method that goes through all the expressions in the array list, and for each expression where the expected result is equal to the calculated result, it adds 1 to the fitness and returns that fitness. And we will have a generate expression method that takes in a postfix string expression and an expected result and a number of operands, and returns an instance of expression. So this will be the return expression that we end up returning. And we'll define a stack of expressions, and we will use space to pick up the different tokens in that string expression, and we'll define a left expression and a right expression. And while we have tokens, we'll check if that token is AND or exclusive OR, and in that case the left expression will be the value of stack.pop, and the right expression will be the value of stack.pop also. And we will push onto the stack a new expression, and we instantiate that expression with the left expression, the right expression, the token, and the number of operands. Otherwise, if we have a number, then we push onto the stack a new expression with the value of that number. And the return expression would be the value of stack.pop, and we will set the expected result for that return expression and the calculated result by calling return expression dot calculate result. So this should do it for this class. Next, let's go to the genetic algorithm class and define those constants. The mutation rate, we'll set it to this value for the purpose of this tutorial. Same thing for the crossover rate, and the term and selection size, and the population size. Here it is 6, and the number of elite groups for the purpose of this tutorial, we'll just not have any elite groups. So the population will have an array list of groups, and the size of this array list will be the population size, and we'll have a get method that returns that array list, and we'll have this Java 8 method for sorting the groups in the array list of groups, so sort by fitness. Does it this way, and we need to randomly generate operators given the number of operands. So we'll have this method that does that. So generate random operators. It takes in the number of operands, and since here we have 5 different operands, it means we're gonna pick up 4 operators randomly, and we do it from here. So we select them from this array list, and we append them to this string buffer and return a string containing those operators with space in between. And finally we'll have 3 different constructors. So a default constructor, and one that takes in an instance of population and returns a new instance, and the third one takes in a population size and a number of operands, and generate random expressions for each group of expressions, and adds the operators to the operand for each expression in the group, and this will be the expected result coming from here. And the number of operands. So this should do it for this class. Next, let's go to the genetic algorithm class. And we'll have this crossover population method that takes in the population and, for convenience, number of operands, and does a crossover for all groups in the population. And we'll have another method that does mutation to the passed in population and returns a mutated population. And we'll have this evolve method that evolves the population by calling crossover population, and what's returned from that, it calls mutate population on it. And we will be using tournament selection for crossover. So we'll have this select tournament population, that takes in a population and for convenience number of operands and return the selected tournament population. In this case it will contain two groups. And the crossover population will end up calling this crossover group method, passing in two groups to do crossover on, and for convenience the number of operands. And the mutate population will end up calling this mutate group method for each group in the population. Now here we will define this crossover population and return it. But before doing that, we will move the elite groups as is to the new population to be returned, the crossover population. As for the other groups in this passed in population, we will call select tournament population and get the fittest one from that population, and this would be group 1, and then call it again and get the fittest one, and this would be group 2, and then we would do crossover population dot get groups, and we will set the crossover of group 1 and group 2, and we will repeat for all remaining groups in this population, meaning that are not elite groups. Now for mutate population, I'll define this mutate population and return it. But before doing that, we will move the elite groups as is to the new population, to the mutate population. As for the remaining groups, we will end up calling mutate group on each one of those. Now for select tournament population, we will randomly pick up groups in the passed in population, in this case two groups, and put them in this tournament population that we defined, and sort them by fitness and return that tournament population. Now for mutate group, we will be returning the passed in group after mutating it, and we will only perform mutation if math.random is smaller than the mutation rate. And here we will randomly pick up an operator to be mutated, and this will define its position, and this will be the original operator. And I will make sure that the replacement operator is different than the original operator. So now we have a new operator that we'll use for replacement, and we will go through all expressions in this group, and we will define a string buffer and append the new operator in the postfix expression in place of the original operator. And we will have new expressions in place of the old ones, accounting to the new operator. And this will be the mutated group that we will end up returning. Now for crossover group, let me define this group instance and return it. And this instance will contain the crossover of group 1 and group 2 if it is performed. And let's pick up a random number between 0 and 1. And for all expressions in group 1, we pick up one of the expressions and we define this string buffer instance. And we will not perform crossover in case the crossover rate is smaller or equal to the random number that we picked up over here. So we will append the postfix expression as is to this string buffer, and we will add it to the crossover group and end up returning this crossover group, which would be actually group 1 unchanged. So if this is not the case, then we will perform crossover. So here we will pick up all the operands for this expression, and we need to add to it the operators, and we do it here, and we add those operators from group 1 until this crossover point, and from that crossover point we add the expression from group 2, or operators from group 2, and we end up returning the crossover group. And this should do it for this class. Next, let me go to the driver class, and let me first add the methods that do the printing. So I have this print heading method that prints heading for each population, and I have this print population method that prints the population below the heading for a generation. And this method that prints the group of expressions as a table, and we pass it the group. And going back to main, I'll first instantiate a new driver instance and pick up the number of operands. So we have 5 operands here, and I picked 0, 0, so we end up here, which would be the same for each one, since we have to have the same number of operands. and I use space to separate them in order to be able to call count tokens and count those numbers. And I'll pick up a new population instance, pass it the population size, which is 6, and this number of operands. And I will instantiate a new genetic algorithm and start from generation number 0, and this will print the heading, the population, and the group of expressions as table for generation 0. And this code will go through the remaining generations and print the heading, the population, and the group of expressions for each generation. And I will first evolve the population. And I will finally print the discovered formula in regular notation and in postfix notation. And this should do it for this class. Next, let me go ahead and test run the application. So actually generation 0 did it. So let's do it again. We went from generation 0 to generation 14, and we ended up discovering this formula in postfix notation, or written this way in regular notation. So for each one here, the expected result is equal to the calculated result, and this table represents this row, and it has 4 different expressions. So we're displaying the expression, the expected result, and the calculated result. Finally, let's try with a different training data. So we went from generation 0 to generation 10, and we discovered this formula, or written this way in postfix notation.